Chapter 14, Topics 14.1 to 14.3, Kinematics of Particle, Work energy for a system of particles. So before we go through this presentation slides, I will explain the concepts of work and energy through a couple of examples, and then we will go back and revisit the presentation. In this example, you can see that a table or the desk is in this position. Let's call this position number 1 is not moving. That means the velocity of the table is 0. It has some mass m, but its speed is 0. Now the boy applies some force F towards left direction, and as a result of that the table slides in the left direction and goes from position number 1 to position number 2, where at position number 2 the table is still, or the desk is still in motion. That means it has some non-zero speed or velocity. So its v1 is 0, but v2 is some speed v. So we can say that uh, when this boy has applied the force on the desk, as a result of that, this force has resulted in the displacement of the table. So we can define this instead of velocity, we can also define the position variable as well. So initial position of the table or the desk is S1 and the final position is S2. So this force F resulted in change in displacement or displacement of the desk, and that is considered as the work done. So when a force is applied and as a result of force particle has displacement, then we can say that the force has done the work, and the work done by force can be defined as u going from position 1 to position 2, and that can be calculated by integral of f times dr, where dr stands for position vector, and this is not multiplication, this is called dot product. And dot product can be written as a scalar equation, integral f ds cosine theta, going from position S1 to S2. So this is the formula for generalized formula for work done. So work done by force is force multiplied by displacement multiplied by cosine of angle between the force vector and the displacement vector. In this case, the displacement vector is horizontal, and so is the force vector. So the angle between them is 0. So this, for particularly for this case, it can be written as S1 to S2. Sorry, it's strong here. Yeah, this can be written as going from S1 to S2, f ds, and cosine 0 is 1 because sine 90. So this is the concept of work done. So when a force is applied and as a result of that force, the particle experiences displacement, we can say that the force has done some work. Now, work done can be positive or negative. So work done U is positive if both F and ds are in the same direction. So when the force applied and the work done and the displacement are in the same direction, then the work is positive. Work is negative if F and ds, that is force and displacement, are in the opposite direction. Now, it's the result of work done. What has happened that when particle has moved, its velocity has also changed. Now, particle has energy because of its velocity by virtue of its speed. It's called the kinetic energy, and we use letter T to define the kinetic energy. So kinetic energy of the particle is 1/2 times mass times velocity square. So kinetic energy of the desk at position number 1 is 1/2 mv1 square, which is 0, because table does not, or the desk does not have any velocity. But kinetic energy of desk at position 2 is 1/2 times m v2 square, which is some positive quantity. Let's call it T2. And this kinetic energy has increased because of the work done. Now, together, we can combine these two concepts, the work done and kinetic energy, and derive the formula for work energy concept. And as per that formula, work energy concept, initial kinetic energy plus work done by all the forces. There can be, I'm using the sign sigma here. So there can be multiple forces, and work done by some forces can be positive, other forces can be negative. But as a result of all work done, the kinetic energy of the particle changes, and we can obtain the final kinetic energy. And this is the formula that we use to solve the work energy related problem. So initial, number one stands for initial kinetic energy. Number two stands for after force applying, whatever is the kinetic energy of the particle, we consider that as number two. And U12 indicates the work done going from point one to point two. So once again, initial kinetic energy plus work done by all the forces equal to final kinetic energy. Let's talk about the units. So unit for the work done, U, it depends on the unit of force multiplied by ds times cosine theta. So the unit for work done in SI system is Newton meter, because force has newtons and displacement is measured in meters. There is another unit called joule. So 1 Newton meter is equal to 1 joule for SI system. For FPS system, the unit of work done is, force has this unit of pound and displacement has unit of feet. So foot pound is the unit for FPS system. We just write this in the reverse order because it's more common to say foot pound than pound foot. So these are two different units of work done. This is for FPS system, that is foot pound in second system or US customary system, and this is for system of international standards. The unit of work done is Newton meter or foot pound. One interesting fact to notice here that kinetic energy T is 1/2 mv square. Now mass is positive, envelope speed is always positive because this is the magnitude. That means T is always positive. T can be 0 or greater than 0, but T will never be negative. Either it's T1 or T2. Kinetic energy is scalar and it's always positive. However, work done can be positive or negative. Work done is also scalar, but it can be positive or negative depending on whether the displacement and forces are in the same direction or are in the opposite direction. Okay, so this formula will be given to you for problem solving, and it's written here. So initial kinetic energy plus work done is equal to final kinetic energy, and the formula for work done is F dot dr. Now for the next three examples, we will look at the work done by different forces such as externally applied force, spring force, and the weight force. So let's look at few examples. So let's start with here. So determine the work of the force when the displacement of the particle is 2 meters. So this box, when 500 Newton force is applied, as a result of that, the box moves from position S1 to position S2. So displacement of the box is 2 meters. Now, when this 500 Newton is applied, it can be resolved into two components. Horizontal component, which is 3/5 of 500, that is 300 Newtons, and vertical component, which is 4/5 of 500, or 400 Newtons. Now, only this component of the force is in the direction of displacement, so it is only responsible for displacement of the box. However, this component only applies compressive load, and this does not cause any displacement. So work done by this force, U going from 1 to 2, is nothing but F times ds, which is F multiplied by ds, which is 2 meters multiplied by cosine of angle between this vector and this vector, which is 0. So that is the work done by the applied force. So this is like 300 times 2, so that's 600 Newton meter, or you can say 600 joule. We use capital letter J to define unit joule. So this is work done by the applied force. Now this is very straightforward problem, especially when force is constant. But there are cases where force is given as a function of displacement. And if that is the case, then work done can be calculated using integration equation going from S1 to S2, F cosine theta multiplied by ds. So we will use this formula to calculate the work done in the next example, where force is given as a function of displacement. So let's work on this example. So let's say that this force is 100 s. It's not 5, it's s. So it's 100 multiplied by s, where s is the displacement, and this angle here is 30 degrees. And as a result of this applied force, the box has displacement of 2 meters. So let's say that box goes from position 1, which is S1, to position 2, which is S2, and this is 2 meters. So calculate the work done by this force. Now, because the force is not constant, we need to use integral sign. So U12, work done by this force, applied force F going from 1 to 2, is integral of S1 to S2, F cosine theta ds. Now, if we define that this point is the origin, that means S1 is 0 and S2 is 2 meters. Then we can substitute the limits of integral 0 to 2 meters. F is 100 s cosine 30 ds. 30-degree angle between the force and the displacement vector. So now this can be written as 100 times cosine 30 is 86.60. So we can take this out of integration, 86.60, and inside the integral is 0 to 2 s ds. Now integral of s with respect to ds is s squared by 2. So this is 86.6 s squared by 2, 0 to 2. So substitute s squared equal to 2 here. So it is 2 squared by 2, which is 2. So the final answer is 173.20, or as a three significant figures, it's 173 Newton meter. That is the work done by the force, U12. So remember, work done by the force, you need to use this integration and calculate the work done when F is given as a function of displacement. If F is constant, then we can directly use the formula F ds cosine theta like this and calculate the work done. So this is when force is function of displacement. Now let's look at the other types of forces, such as spring force. How do we calculate the work done by spring force? So let's consider spring here. Let's say this is the initial position of the spring, and this is S1. Now when force F is applied at the end of the spring, let's say someone pulls the spring and stretches it so that the spring changes the length from S1 to S2. And this is like external force. But then spring itself applies the force when the external force is applied, and that opposes the externally applied force, and we call this spring force, or Fs. And let's say the spring has the spring constant K. So how can we calculate the work done by spring in this case? So work done by spring is actually negative because the displacement of the particle, this end of the spring, stretches in positive x direction while spring applies force in the negative x direction. So both displacement and spring force are in opposite directions. So work done by spring is negative, and we can calculate that as F spring going from 1 to 2 is minus 1 half K time S2 square minus 1 half K time S1 square. This formula will also be given to you in the equation sheet, where K is spring constant, S2 and S1 are final and initial lengths of the spring respectively. So when you substitute all these numbers here, you can calculate the work done by spring. During stretching, however, let's say that this is the initial condition of the spring. The spring is already stretched, and then if we release the spring and allow it to contract, and go from S1 to S2, then when you apply this formula, U spring going from 1 to 2, you will apply the same formula, get the same distances and everything, but this work done will be positive, because in this case the particle spring stretches, or spring, when spring is released, it goes from right to left, and so is the particle attached at the end of the spring. So work done by spring is positive in this example. So there are two concepts for spring. Work done by spring during stretching of spring is negative, but work done by spring during release of spring is positive. So depending on the problem statement, you will get either positive or negative number. Third type of force that we consider is the force of gravity, or the weight. So what is the work done by weight? So in this example, you can see that this person bungee jumps from certain height, and when person bungee jumps, the force that he or she experiences is because of the work done by is because of the gravitational pull. So what is the work done by gravity in this case? Because if we consider this person as a particle, then particle is going from some height h1 to another height h2, and what is work done during that period? So let's look at the another example, that this is, say, a 50-foot tall building. Okay, and there is a person throws a ball from this 50-foot tall building, and the ball hits the ground. The ball has or an object has mass of 5 pounds. It's not ball, let's call this an object. So person throws an object which weighs 5 pounds from 50 feet tall building, and it hits the ground. What is the work done by gravity during this motion? So let's define y-axis, vertical axis. So work done by gravity, we can call that uw, going from position 1, which is this, to position 2, is w, weight, multiplied by displacement. But in this case, the displacement and the gravitational force, they are in the opposite direction. So gravity force is in the downward, they are in the same direction. So gravitational force is in the downward direction, and the displacement is in the downward direction. So we can say that the work done is nothing but weight of the object, which is 5 pound, multiplied by displacement, which is 50. So 5 times 50 is 250 foot-pound. So this is work done by gravity, UW 1 to 2. However, if you consider a different case or different scenario, where a person is on the ground and that person throws an object upward in the air by 10 foot, and that object weighs 5 pounds, what is the work done by gravity in this example? So UW going from 1 to 2. Now 1 is here and 2 is here. So for this case also it's W delta Y, but the work done is negative, because gravity is always like applies in the downward direction, but the displacement of the particle delta Y is in the upward direction. So since they are in the opposite direction, work done is negative, and that is 5 pound multiplied by 10 foot, so it's minus 50 foot-pound. This is work done by gravity, UW12. Okay, so so this is, let's summarize what we have discussed so far. So we have understood the concept of work done, that work done U12 can be calculated in generalized equation as F cosine theta multiplied by ds, where ds is displacement, theta is the angle between F and ds, and F is the applied force. Now, work done by spring can be positive or negative depending on whether spring is getting stretched or spring is released. Work done by gravity can be positive or negative depending on whether an object is traveling in the downward direction or the upward direction. And if we have all these different elements, spring or externally applied force or the gravity in our system, then we can say that as a result of all these different forces, the kinetic energy of the particle T1 changes to T2. So T1, initial kinetic energy plus work done, is equal to final kinetic energy. So now we can go back and look at the presentation. Today's objective: calculate the work of a force and apply the principle of work and energy to a particle or system of particles. So in this slide, we can see that there are different forces that are being applied, and that's the free body diagram for the block. When force P is applied, the block is traveling from S1 to S2. However, the displacement of the block in horizontal direction, so forces which are doing work here are only these two forces, applied force as well as the friction force. Now, applied force and displacement are in the same direction, so work done by P is positive, but work done by friction is negative because friction acts in the negative direction. And there is no work done by W and N because they both are perpendicular to displacement. So whenever a force is perpendicular to displacement, the dot product of that is 0. Okay, so this is the quick recap of dot product. So if there are two vectors A and B, then the dot product can be written as vector A dot product vector B is equal to magnitude of A magnitude of B multiplied by cosine theta. And when you apply the dot product concept to work done, then this is the formula for work done, F ds cosine theta. Or in the integral form, it is R1 to R2 F dr or S1 to S2 F ds cosine theta. Remember that R is for vector and S is the scalar or magnitude of that vector. So in this case, we can see that when force F is applied, it results in displacement of particle from S1 to S2 that can be calculated using this formula. Now, concept of principle of work and energy. So when the work is done on the particle, as a result, its kinetic energy changes. And this is a scalar equation. So initial kinetic energy plus work done by all the forces equal to final kinetic energy. The unit of work done is joule. 1 joule is 1 Newton meter or foot-pound for FPS system. These are a few examples where you can try to calculate the work done and see if you can get the correct answer. So for the first case, the work done is 0. For the second case, work done is 100 times 2. For the third case, work done is 100 times 2 times cosine 45. For the fourth one, its force is given as a function of position. So you can calculate work done by integral 100 s ds cosine theta. And for the fifth example, the work done by 100 Newton force is positive, which is 100 times 4, but the work done by friction is negative because it acts in the opposite direction. And for all the blocks, the mass is 3 kg and coefficient of friction is 0.3 for the last one. We do not need to consider the friction in other examples, other previous cases. Only for the last one, consider the friction force or coefficient of friction as 0.3. So quick recap of what we discussed here. So when force and movement of particle are in the same direction, then the work is positive. Now they both can be in positive x direction, but negative x direction, it doesn't matter. As long as they are both this arrow are in same direction, work done is positive. When these arrows are in opposite direction, force and movement, then that work done is negative. Okay. So what is the work done by force F in this squeeze? So force is applied here, displacement of the particle is perpendicular to that. So what is the dot product of two vectors which are perpendicular? And the answer is 0. If particle has curvilinear motion or motion along the curved path going from point 1 to 2, then the work done can be calculated. We can separate this resultant force into tangential force along the tangential axis or normal force along the normal axis. Normal force is perpendicular to displacement of the particle. That's why it's called normal. So what do you say about the work done by normal force? 0. What do you say about the work done by tangential force? In this particular case, particle is going from 1 to 2. So what is the correct answer? You can pause the video and try to guess the answer. So this force is in the direction of displacement. So work done is positive, and it's this S1 to S2, sum of all the tangential forces multiplied by ds. Now, few practical applications and examples of work done. So in this case, we can see that the roller coaster car goes from point A to point B and it completes the loop. Now going from A to B, there is change in elevation. Well, let's call this delta y. So depending on the weight of the coaster, the work done by gravity is positive, W multiplied by delta Y. Now, in order for the coaster car to complete the loop at B, it must have certain kinetic energy at B, because if that kinetic energy is not enough to overcome this loop, then it may possible that the coaster car does not complete the loop and maybe like just bounce back from certain height. So based on the height of B, engineers when they design the roller coaster, they calculate the height of A so that the work done by gravity W times delta V gives enough kinetic energy to coaster car when it reaches at the bottom of the loop, so that it can go all around this loop B and overcome through that like peak point and continue its motion in the forward direction. So in order to design this, concept of work and energy is applied. So this is clearly the case of kinetic energy and work done. So initial kinetic energy at the top is, let's say, 0. Kinetic energy at the bottom is certain value depending on the work done, and that kinetic energy helps to complete the loop. Another application example, crash barrels are often used along the roadways in front of barrier for crash protection. So this drums here, they actually act as spring, as shock absorber when vehicle at high speed hits those objects or hits those drum. So if we know the mass of the car and maximum speed of the car, and if we would like to have these drums absorb all the kinetic energy of the car such that after accident car stops moving, then based on that information, so car has initial kinetic energy T1, which is 1 half mv1 square. Car's final kinetic energy is 0 because we want the car to stop after hitting those drums. So based on this equation, T1 plus sigma u equal to T2, we can calculate the work done by the spring, by these drums. And that work done has force times displacement into it. So depending on how long are these like barrel barriers, or how much we want the barrel barriers to get compressed during an accident, we can calculate the required force that they need to absorb. And based on that, we can design the barrel barrier spring coefficient. Okay, so this is practical application of work done. Now, that's the same slide that we have seen previously about the work done. Okay, so work done going from S1 to S2 is delta S multiplied by cosine theta multiplied by Fc. Work done by gravity or weight is negative if particle goes from S1 to S2. So it's moving in upward direction. So work done by gravity is negative in this case. But if the particle is moving in downward direction, then the work done by gravity is positive. Work done by spring, we already have discussed this formula. So this is the equation for work done by spring, minus 1 half k s2 square minus 1 half k s1 square. And remember that this is different from spring force, which is k times s. And that's the final equation, T1 plus sigma u equal to T2. Now work done by all the forces can be either positive or negative, but T is always positive. Kinetic energy is always positive scalar quantity. And using this equation, we can solve problems such as roller coaster or barrel barrier problem. And that's what we are going to do in the next video. So